All right, and we are live. Hello, Andy. How are you doing?
I'm very good, Yuka. How are you?
I am good as well and excited for the first official Quanscient webinar of the 2025 fall. Isn't that right?
Can't believe how quickly the year has gone in.
Yep, and what better topic to kick it off than with our beloved MUTs? How about that?
Yeah, you're very patient with me, continually requesting to do more topics on MUTs. Hope the audience today feels the same as I do about that.
We indeed hope so. Uh, I appreciate everyone who has joined in time. We'll just wait one more minute before getting into the actual topic. But again, thanks for all the diligent and timely people out there. All right, now the rest will come when they come. But all right, so indeed, we are talking about accelerating MUT design with cloud-based multiphysics simulation. And let me just kick it off officially with this slideshow as usual. So here we are. Now, just for some context, this webinar and the demos and the case examples that we are covering here, uh, we sort of covered them in our December webinar, which was such a hit that we are actually revisiting them right now. So if you were attending live last December on the 17th, uh, you likely have seen this stuff. Doesn't mean that you have to go away, but there's just likely nothing new for you here. But if you were not live on December 17th, I hope you stay live since we are going through some very nice cases here. So, all right, a couple of things, housekeeping items, just to get these out of the way. So we have this questions tab at the top, so you can submit your questions at any time, and we will be addressing them throughout the webinar. And we will also be handing out some resources in the materials tab you can see in the top right-hand corner as well. We'll get into those soon. Who we have talking here is, my name is Jukka Knutinen. I work as the head of marketing, and then we have our special star for today, Dr. Andrew Tweedy, our co-CTO and co-founder. Andy can get into a bit of his background if he wants to very, very soon. Okay, after introduction, after a quick these welcoming words here, Andy will get into some challenges in MUT design with traditional tools, then into some, well, not necessarily live demos, but basically the results of these demos, so the actual interesting part there. We'll go into some CMUT stuff, Q&A at the end, and leave you with some conclusions and key takeaways. Now, this is what we will be handing out. So as said, since we did cover these case examples already in December, we have the PDF summary already pre-packaged for you. So at the end of the webinar, this is what we will be handing out. So don't go anywhere. Now, quick, before we get started, before we go into just a couple of slides on what Quanscient is, what Allsolve is, so basically the context of today, I'm just gonna put a quick poll asking how familiar are you with Quanscient? Now, if whether it's the first time you're hearing about it, heard of it sometime, somewhat familiar, quite familiar, or very familiar, just so we can grasp sort of the crowd today. So how familiar are you with Quanscient? I'll just give you a minute or so to cast your vote, and then we will move forward. All right, first answers getting in. Some are very familiar. A couple I've heard from it. No one's first time yet. Don't know if that's a good thing or a bad thing, but no one's first time so far. All right, seems indeed that there is It is the no one's first time hearing about. Some have heard, and some are familiar, quite familiar, very familiar. Let's end the poll after 1 minute here. Share the results looking like this. Okay, so won't bore you with the Quanscient details, just a quick overview. So indeed, a cloud-based FEM multiphysics simulation platform developed by Quanscient, which is a Finnish company or headquartered in Finland, founded in 2021, with the value proposition of a natively coupled multiphysics built to scale. Now, we have indeed customers in both industry and academia, just to mention a few here. And then we have these key advantages in MEMS design. Now I listed a few of them here, which look like this. But I thought that instead of me actually going through these in words, what Andy will show here will actually present these in real life. So we'll look at increased simulation throughput, test with real world conditions, comprehensive multiphysics modeling. Not sure about the API stuff or the workflows, but at least all of these here. So I won't bore you with words, but we'll let Andy excite you with the real stuff. So that's it from my part, and now let's get into the meat of the thing. So Andy, you are on.
Thanks, Yuka. I think you need to make me presenter.
Indeed. There we are.
Lovely. Okay, so as Yuka said, I'm going to start by talking a little bit about the challenges that as MUT designers we face. It's not an easy area. The simulations are challenging, and that's really why it's one of the areas that we feel Allsolve can offer a big upgrade to engineers compared to other FEM simulation tools. We'll talk a little bit about some of the things that we're doing in PMUT and then move on to CMUT. And then we'll have, I hope, a good opportunity today for any questions that you want to ask us around what we're doing. So maybe before moving on, just a short background from me. I started off in sonar design. So I originally designed piezo composite phased arrays for ultrasound sonar. Did a lot of work in NDT and also biomedical in those areas. And particularly through the biomedical work, got more and more into MUT design, various other MEMS. And over time, I've gone from mostly working in device design through to being really for the last 10 plus years completely focused on simulation of not just ultrasound, but variety of other designs. So this is an area that I've spent a lot of my career on, and probably, in all honesty, the one that I like to geek out on the most. So before diving into exactly what we do, I like to try to set a bit of context. Why is this a topic that we want to talk about? Why is it something that perhaps engineers that are working in these areas need better tools for, more help with? Well, the first thing to cover is it's a really important area, a very impactful area. When putting these slides together, I sneakily grabbed a couple of sections from Professor Directivity at Georgia Tech's excellent IEEE Spectrum article. And it talks about basically how medical ultrasound in the last 40 years plus has gone from this kind of thing through to this. And there's a lot of things we work on as engineers that have big impacts, but when you see the kind of human impact that this kind of point of care ultrasound, point of care diagnosis can really have, it really grabs the imagination. So it's an area that I care a lot about. So why are these devices challenging to simulate? Well, they're geometrically very detailed. We've got complex devices, very thin layers, potentially arrays of many thousands of MUT cells, potentially hundreds or even thousands of individually addressable elements. That's one of the things that MUTs allows us to do, integrate sensors very closely with the electronic drivers and receivers. So it lets us push the element count up. The simulations themselves, when it comes to FEM, can get computationally very large because of these things. There's often a large array structure with potentially quite a large acoustic load in front of it. So we can easily see MUT arrays with tens or even potentially over 100 million degrees of freedom. And these aren't, especially when we consider these are multiphysics, highly coupled simulations. These aren't simulations that traditional FEM packages are well placed to handle. The other aspect is because it's, right, we all know that MUTs aren't new. If you look at the history, MUTs have been around for since at least the 90s, but it's really only in recent years that they're making a major commercial impact. So taking the flexibility and the complexity that can be involved with the structures and combining that with the fact that there's a lot of interesting avenues of design to explore, there is a lot of room for innovation. And ideally, as engineers, we really want to explore this design area. But to do that, we have to run many simulations. We'd ideally like to be able to consider thousands of different designs and evaluate their performance against each other. And again, that's very challenging to do with traditional FEM packages. So these are the things that Allsolve is addressing, and we'll touch on this more as we go along. The other thing to throw in is that while PMUTs can, for a large part, be considered as linear devices, we know that CMUTs, with their DC biasing, are inherently nonlinear devices. So there's another level of complexity in their simulation, which adds to the difficulty. And just to expand on the sort of dimensions that can be encountered in simulations, here is let's say a typical linear array. Let's say this is being used for diagnostic imaging. It might have 64 to 256 elements. But regardless of whether we're using MUTs or more traditional piezo-composite devices, there are a huge amount of MUT cells, pillars, huge amount of detail contained in each one of these elements. And that makes FEM models of these devices particularly huge. So when we approach simulations of arrays, we like to do it on a step-by-step basis, starting with basic single cell models of the device stack up, moving through various cross-sectional models of the device, and then if necessary, simulating large 3D sections of MUT arrays. And just to illustrate what's possible there, this is a PMUT array simulation done in a transient simulation with, I think it was just over 700 MUT cells. So that just shows you what is possible in terms of scale and scope. Now, I attended MUT 2025 in Tours a couple of months ago, gave a short presentation of that. There was a lot of really interesting work presented at the conference, but there was really nothing in terms of this scale in MUT simulation. So when I say that we are pushing the boundaries of array scale MUT simulation, this is the sort of thing I mean. So what we're going to do next is go into some more detailed examples of some of the things that we're doing for PMUT and then for CMUT. But before we do that, Yuka, I think we had another poll that you wanted to put to the audience.
We indeed do. So just some further context, some let's say intelligence here. So first question is simply to grasp: do you currently use simulation for designing MUTs? Now, this is just a simple, basically a yes or no question. And I will share also the results of these polls after we got a decent amount of answers. So let's just see how the audience splits between this. And if I need to remind, there are no right or wrong answers here. All right, just a few more seconds if we can get some answers in. Currently, there's both some no's and a yes there. All right. So with this sample size, we have just one yes and three no's. That's completely fine. Well, then the other question is, and people who didn't answer that can also answer this. So if you do, how many cells do you typically simulate? We got some interesting responses on this particular question last December, and the results of these are actually in the PDF summary we will hand out, and they might surprise you or they might not, depending on your information. But let's see what we have here.
Yeah, there was definitely a good variation, a good spread last time we asked that.
Yep.
Oh, someone's confident. Someone's all over this.
Oh yeah, there is a whole array answer right there. One person said a few. All right, just a few more seconds. See if someone else wants to answer before we put out the results and move forward. All right, just a couple of answers. One person a few, one person got this with the whole array. All right, thanks for the answers, and back to you, Andy.
Thanks, Yuka. Okay, so let's dive into some PMUT case studies. So the array that I'm going to use as an example here was taken from a paper from Professor Horsley's group when he was at BSAC in Berkeley, and it was a early PMUT fingerprint sensor which you can see here it's got a silicon elastic membrane layer, a aluminum nitride piezo layer, and it's stacked on a silicon dioxide wafer with which then bonds onto the CMOS wafer through some electrical interconnects. The paper mostly discusses this being used for fingerprint sensing, and most of the work in the paper looks into a PDMS load because they're trying to replicate basically a tissue mimic. But what we did here was look at it as if it was a medical type array being used for medical imaging. So we looked at it operating into a water load, which is very close to the design load, so we can get some sensible results out. So I mentioned different types of model and building up capability. Building up complexity. The way we would always start looking at one of these devices is by simulating a unit cell, or essentially a single cell model. The reason we call it a unit cell is it's often possible to model a half a cell or even a quarter of a cell, depending on the symmetry of the device. So it's really the smallest section of your array which defines the repeating pattern in the array. And this gives you a really good approximation of what an infinite array of MUT cells would look like, which coincidentally, in the early stages of testing, is often what we measure either on our impedance analyzer or in an experimental setting like a wet bench or maybe a laser vibrometer. So this can be a very good starting point to start to understand what the fundamental performance of a cell is going to look like. And we're going to pull out outputs that could be directly compared to many of the measurements that I just mentioned. We're going to show harmonic and transient results from this. Oh, sorry, I've commented that I think the slides I've got here are just for the transient results. I'll not dive into meshing in a lot of detail, but safe to say that there are a lot of different meshing options in Allsolve. So it is a true multiphysics general FEM package. So we're not saying, hey, we're able to simulate these large arrays because we've taken a stripped down, say, finite difference approach, or even a explicit FEM solve with a structured grid, which are potential ways of accelerating a narrow range of ultrasonic simulations, but they don't offer the broad flexibility that a general approach like ours does. So we're implicit, when we do transient simulations, we're implicit transient. We can support arbitrary meshes like the ones that you see on the screen. And that gives us a lot of flexibility to really include the detail and the geometry, and also the flexibility to include pretty arbitrary device physics where necessary. So here's some very basic outputs from that unit cell model that we looked at. We've driven it here with a short wavelet voltage pulse, and you can see the corresponding current on the drive electrode. You can also see through the animation here, so that we're looking really at the back side of the device here with the water load beneath it, and you can see the displacement field in the structure itself, and then the acoustic wave leaving through the the water load. We have a PML at the bottom here to absorb that wave and approximate an infinite body of water. And some more time domain outputs that we could look at here. This is the displacement. I believe in this case it was at the center of the cell, but sometimes we like maybe plotting something like the average surface displacement. This one's quite useful because it could be compared directly to, for example, a laser vibrometry measurement. And this is pressure in the load, just at the base of the load here. Another thing that we'll see as we go on to look at more complex models is we quite routinely use Kirchhoff extrapolation to look at far field responses of MUT and other ultrasonic devices. It's usually attractive to keep the FEM simulation quite small, but once we're into the acoustic load, we can then use Kirchhoff extrapolation to look at distant field points, distant outputs, and we can do this in both transient and harmonic simulations. You'll see from the metrics below that this is a really compact model. So it runs in less than 60 seconds, it consumes very few core hours. So it's a very efficient way at simulating the fundamental performance of this stack. So okay, let's assume that we've run maybe thousands of those simulations. We've got a better idea for how our design performs, and we want to start to look at array level performance. Well, in our linear array example here, something that we might want to do is simulate a single element of the array and potentially look at the output of that in the far field, maybe recreate some things that we would measure in a scanning tank or a wet bench, as it's sometimes called. And in this case, we're going to simulate the elevational beam pattern. So we've got a full element here. We're going to apply symmetry to these two long dashed lines and also this shorter dashed one. So we're simulating driving a large array of these elements and trying to understand what the elevational beam pattern would look like. And in this case, we're going to do this CW, so we're going to use a harmonic analysis to do that. And this is what it looks like. Here's the displacement and pressure fields. Again, we're looking at the back of the array here, so we can see the displacement in all of the MUT elements. This one's at the center of the array. We've applied symmetry in that direction. And you can see that at the end of the array, now they're not particularly significant here because it's a long element, but we can see that there's a slightly lower displacement here. So we're seeing those length effects on the element. We're seeing the effects of the end of the element and the start of the substrate and how that loads the last cell and influences the surface displacement. And when we plot I've called it a vertical beam pattern here, but elevational beam pattern might be a more proper term. We can see that we've got, as you'd expect from a long array like this, a very narrow beam. Again, this is a relatively fast simulation. We're running this in under 60 seconds, even though it's somewhat more degrees of freedom, but it's a harmonic solve as opposed to the previous solves where we're transient with many time steps. Final cross-sectional model here is taking an azimuthal slice, and what this is really useful for is simulating crosstalk, which I think a lot of people in the field are interested in. But as I say, there's not a lot of simulation tools that can really do this effectively. So I really like cross-sectional models in the azimuthal direction because it gives you really quite a lightweight model to analyze the azimuthal beam pattern and also crosstalk effects and come up with design features that might suppress crosstalk and give us a broader and potentially smoother azimuthal beam pattern. So again, the dashed lines are all lines of symmetry. So essentially what we're doing here is we're driving a central line of elements, and we're leaving these 1, 2, 3, 4, 5, 6 adjacent elements passive. They're not being driven. And we're going to be able to observe any crosstalk that propagates across the array and would potentially interfere in a linear array with our ability to steer the beam throughout some sort of body. What we've got here, again, this is a harmonic output. So at the center frequency of the array, this is plotting that surface displacement. It's as if we did a line scan on a laser vibrometer, plotting it on a dB scale. And we can see that 1, 2, 3 adjacent elements have maybe some sort of elevated level of crosstalk. And then as we move out to the outer elements, that settles down to a relatively low level. Now, it's not a huge amount of crosstalk. There are definitely arrays that have more crosstalk than this. But here we can see the effects of that on the azimuthal beam pattern. So you can see that in terms of 6 dB beam width, we're still way over plus or minus 60 degrees, which is pretty good. But you can see that there's some ripple in there. Engineers who are designing beamforming algorithms might have placed a spec on the level of ripple that can be tolerated in here for a given image quality. So that might be something that's in our spec that we need to be able to work towards. One thing I will say is that harmonic simulations will always exaggerate these interference patterns. We would expect that running a transient simulation would result in somewhat smoother behavior here. And then finally, after having run these two cross-sectional models, gained some confidence, maybe refined their design somewhat, we can move on to really a combination of those two previous simulations. So we've got a full line of MUT cells along the dashed line, which are going to be driven here. And then again, we have 6 passive elements on each side, which aren't going to be driven, and we can observe crosstalk on. And here's some transient results from that simulation. So again, drive voltage and current. We could easily plot charge here as well. We've run this time on 32 cores on the cloud, and it still runs in 15 minutes. Really quite a compact model for an array of this sort of scale. Here we've got a little bit like what we saw in the unit cell model, the surface displacement, and then acoustic pressure out in the load. There's obviously various ways we could plot that. We could plot that at particular points, or we could plot an average, or indeed we could plot that at a distant extrapolated point. And
by the way, sorry to jump in.
yeah, go ahead.
But just as a reminder for everyone, if at any point you have any questions of what is being shown, or something is puzzling, or you just want clarification for something, the questions tab is open, and the questions are anonymous, so no one else will see the questions except for Andy and I. So just a reminder, back to you.
Yeah, good point, Yuka. Thanks for that. So I already teased this earlier on in the slides. This was indeed, when you saw this earlier, this was the result from this full 3D array section. And that's as a transient simulation here. And then, of course, we could also do that as a harmonic simulation in CW. So there's lots of options. You can choose the option that best recreates your lab measurement techniques. That's what we're always looking for, to be able to recreate and then ultimately to predict experimental results, predict performance in real world situations. And final set of outputs from that 3D array section are both the azimuthal and the elevational or vertical beam patterns. And these look very, very similar to what we were able to achieve with cross-sectional models. So the message that I would emphasize here is, when you can run cross-sectional models, it's a really good idea. It's a really direct and lightweight route to get you a lot of valuable information. The thing to bear in mind is that there are sometimes secondary effects that a cross section can't capture, and there are also some geometric designs and structures that they can't fully capture. So it's important to choose the right tool for the job. But I would always aim to run a lot of cross-sectional models for every very large 3D model. That usually is the best way at arriving at a good design. So that caps off everything that I wanted to talk about for PMUT. I'm going to show a very quick set of slides, some of the work that we were doing towards the end of last year on CMUT. Now, since then, we've covered a lot of ground on CMUT. We've got a really nice case study on that as well. So if CMUT is your area and you'd like to see more of what we can do there, I'd really encourage you to reach out, get in touch, and we can share some more slides on this. The idea of this webinar was that it was a simple rerun of what we talked about in December last year. So we've stuck with the same material here. So like PMUT with additional challenges is what I've said. They're similar structures. Obviously, we know that in PMUT we have piezoelectric actuation. In CMUT, it's electrostatic. So the physics is slightly different. That's not a problem. Our solver is a very generic multiphysics approach, so we can cover all of these effects. But the additional complexities that I mentioned earlier of a static DC biasing stage, and then the fact that the behavior is nonlinear, and potentially if we're operating in collapse mode, there's also nonlinear contact, makes CMUT simulations quite a lot more complex than PMUT. So this is a very simple example, based on some geometries that from some papers from DTU Nanotech in Denmark, who I did some work with many years ago. What we've got is a very basic CMUT structure with a silicon membrane on a silicon dioxide substrate. First, we're going to do some DC bias stage, and then we're going to look at some of the field outputs from that. So this basically shows the reference design from the paper that we just linked compared to the Allsolve simulations. And you can see this is the pull-in curve. So this is bias voltage normalized to the pull-in, and this is deflection normalized to the cavity depth. So you can see that we get this classic pull-in curve where it very suddenly snaps down at the end. This simulation wasn't set up for full collapse mode, but something that we're starting to do with our contact conditions is simulate collapse mode CMUTs, and that obviously setting up in that way allows you to completely recreate the full pull-in curve to the point of collapse, which can be quite interesting. I should point out that there was 200 static simulations here, but with our cloud platform, we can run all of these in parallel. So the full simulation sweep can be run in under a minute. It's very trivial to do this. So it takes out all of that sequential effort, let's say, that's required from traditional tools when you're running studies and sweeps. And what we find is that a lot of our analysis we do, we employ sweeps quite readily to explore either different boundary conditions and settings or different geometries, material properties, these types of things. The idea is to cut down the engineering time that's involved in these types of analyses. This is again, a little bit like what we saw for PMUT, what I would call a unit cell model of a PMUT, I think of a CMUT, sorry. We've got a quarter of the cell simulated here. In fact, 2/4. It's a small section like this. And when you flip out the symmetry and plot it, this is the kind of thing that you get. But it's representing an infinite group, an infinite array of CMUTs, and that's a output pulse operated into a water load. And again, we can create similar plots to what was done in PMUT, noting that the run times are somewhat longer here. CMUT with its nonlinearity tends to be a relatively long solve, but our solvers can parallelize that very well using domain decomposition. So what you find is it's possible still to go to many hundreds of elements by dedicating 100 or more cores to the simulation. It's not an easy one to accelerate such that it will run in 10 seconds because there's a lot of nonlinear steps to do. But our parallelization allows large arrays to be done like that without the runtimes becoming commensurately large. There's some quite unique things that we can do when it comes to CMUT. We have a multi-harmonic solver, which can be very effective for nonlinear devices. We use it a lot for MEMS resonators. We use it a lot for MEMS microphones and speakers. And what it means is that you can simulate not just the DC bias and the drive frequency, but potentially the nonlinear content that's generated by the nonlinear behavior of the device. So you would see harmonics if you wanted to plot those. And like transient simulations or regular harmonic simulations, you can do this in you can apply phasing to this. So this is a CMUT array where we've applied some different phasing to adjacent elements. So you could do beam steering, for example, using this type of thing. So there's a lot more that we can show in CMUTs. There's a particularly interesting case study that we hope to cover in future webinars. But for today, that is the technical content that I wanted to showcase to you. So with that in mind, we'd be really happy to take any questions that you have. I think we've left some time for discussion, so feel free to ask away.
Indeed. Well, the first question is here, and I guess we could quickly cover this question. Then I will provide the PDF summary for anyone who has to leave, since the question and answer section might take 5 minutes, might take 15 minutes. But the first question, what damping / attenuation models are you implementing in Allsolve?
It's a great question. We commonly use Rayleigh damping, viscoelastic damping, though mass proportional damping. So these things are all pretty readily available. But in terms of the ability to write custom damping models, all of our models have an underlying Python script which defines not only the model setup, but also the physics, the outputs. So all of these things can be customized. So if there's other damping models that are of interest, these can be pretty readily incorporated.
Hope that answers that. Now, that being said, the materials tab has been updated, so you can find indeed the PDF summary from there. So again, it's in the upper right hand corner, materials, and the MUT's webinar PDF summary is downloadable from there. The next question could be something that we get asked quite often, especially in this context, which is how does Quanscient Allsolve differ from OnScale, doing the same kind of things?
Yes, we do get asked that a lot. So I didn't mention at the start, but I was a co-founder of OnScale, so I'm somewhat uniquely positioned to compare and contrast between the two solvers. I touched on this slightly earlier. OnScale was a purely transient explicit FEM solver. So, and it used a predominantly structured grid. So in terms of MUT simulation, that comes with some limitations. If you're trying to simulate very thin layers, what you see in an explicit solver is the time step for the model is governed by the shortest time difference between nodes. So if you have a very small distance between nodes in the model, it means you have to use an incredibly small time step. That was always one of the challenging things I found, particularly for particularly for CMUT, where you're already doing quite an expensive nonlinear solve. If you have to do that across 100,000 time steps because you've got a 5 nanometer layer in there, it can be pretty slow. The other challenge with a structured grid approach like that is that it's challenging to recreate curved structures accurately. So in any circular or even perhaps oval MUTs or designs that have been studied quite recently, the ability to recreate that curves is challenging in a purely structured grid approach. You end up with what would be called a stair-stepped mesh. So mesh flexibility is a challenge there. And then the other one is purely OnScale was written to do some specific things. Those could be accommodated by the solver, but there was no ability to customize, for example, the physics or the damping, as we discussed in an earlier question. With Allsolve, we can edit all of those things, we can modify them, and it gives us a huge amount of flexibility for really exploring new things testing new approaches. So it makes it a much more flexible approach overall.
Now, here's a slightly less technical question for you, but how does onboarding also look like? So how hard or not hard is that? And then sort of joined to that, does adopting also mean rejecting every other tool, or does it replace the tech stack completely?
Yeah, okay. Yeah, those are both good questions too. So in terms of onboarding, it's really, I have to say, it's so much easier in Allsolve being a cloud native FEM solver compared to, I can generalize here, traditional engineering simulation tools. Yuka, you have not had to deal with this pain, but in my past I've had to deal with license files, downloading packages that are difficult to install, setting up license servers. I have lost too much of my life in these things. For a cloud native tool like Allsolve, you simply create a login, sign up, and you log into your account and you get moving. There's no licensing to set up, there's no installation to do. It is much more like logging into an accounting tool or a bank account or any of these tools that we're now used to having online. So from my perspective, it feels like a step in the right direction, and we get a lot of good feedback from our users in terms of the ease of that setup. So your second question, does using Allsolve mean rejecting all other simulation tools? Absolutely not. We're conscious that in many large engineering companies there are licenses available for other simulation tools. They might be used within a given team for other things. They might be the tool that has historically been the tool of choice, and we're quite comfortable coexisting with other solutions, and many of our customers approach us that way. What we really bring in is we're trying to eliminate bottlenecks. So when people come to us and say, "I'm designing PMUT arrays, I have a I have a tape out that in December, and I really need to get the design right for them, and I'm just concerned that with my whatever the current package is, I can only run a few cells at a time, and I'm not going to be able to explore many designs. I can't generate far field array beam patterns. I can't recreate my test results, and my boss has asked me to simulate, explore hundreds of different designs. I can't do that. So we can add that ability to remove those bottlenecks and allow engineers to get to designs a lot faster than previously possible. So yeah, coexistence is definitely something that we see a lot of.
All right. Now, as we still have a few minutes, if you have any questions, any whatsoever, feel free to type them in. We had one last very sort of light-hearted poll just for anyone who would want to perhaps get in touch after we end here, so within the next couple of days, or maybe later, maybe in the next weeks, next months or so. You can just answer your preference here, so we know whether or not to be in touch with you guys. But of course, you can always find stuff more stuff from us at our website quanscient.com. More stuff and resources will be in a follow-up email, including the speaker slides, the PDF summary, and even later on, perhaps the full recording, and links to other resources on our website, including the full-on quanscient.com/mems page that we have. Now, it's a minute for this one. I'll close this too. Thanks for the responses here. And yeah, there was a new question here. Is there or will there be the possibility to include electrical crosstalk?
Yeah, that's possible. We, for many of our ultrasonic sensor simulations, we include electrical components. So maybe in the simple end, a source resistance, but maybe as things get more complicated, maybe some parasitic cabling effects. And yeah, it's possible to consider that parasitic capacitive coupling between elements as well. So yeah, all these things are possible. It's a very flexible approach. Yeah, great question. Thanks.
All right. Last minutes, three minutes. If there is nothing, we would be happy to give a couple minutes back to you guys. Maybe have a quick breather before your next duties or tasks, or to do like me and start your evening relaxation. We do have one question. No, we don't actually. Just a confirmation. So, all right, let's do the former then. So, thank you, Andy. Huge thanks once again for joining this webinar. Thank you everyone who has been joining us here today for all the engagement, all the questions. Andy, anything you want to say as your last words here?
Thanks, Yuka, for setting all of this up, and been a pleasure speaking to all of you. Some great questions there. Look forward to speaking to you directly in the future, I hope. One last thing to throw in, we're going to be attending IUS in Utrecht later this month, which I am thoroughly looking forward to. We will have a booth there. If any of you are attending, don't be a stranger. Love to speak to you in person.
Looks like I got disconnected, but that's a wrap. So thanks once again, and hopefully we'll see you in the next one. Bye.